Students, in this video, we are going to discuss very important topic, extrinsic semiconductor. So, what is meant by an extrinsic semiconductor? Okay. So, why you are going for? In the previous lecture, we have seen the semiconductors are classified into two types. One is intrinsic semiconductor and extrinsic semiconductor. In intrinsic semiconductor, number of electrons is equal to number of holes. Why you are going for extrinsic semiconductor? What is the necessity? Why should we go for extrinsic semiconductor? So, the main reason is in order to increase the conductivity, in order to increase the conductivity, in order to increase the conductivity, we should make the pure semiconductor, or we should dope the pure semiconductor with some impurities. Okay, so what is the main purpose why you are going for extrinsic semiconductor is to increase the conductivity. Okay, so we will see what is meant by doping, why you should dope. So why you should make, for example, first let us take a pure semiconductor. So let us consider this is a pure semiconductor. So I am saying let us consider here three. So this notation in my lecture series, this type of notation I am using for representation of electrons, and this notation is used for representation of holes. Okay, so this is a pure semiconductor. Consider this is a pure semiconductor. What is the condition in pure semiconductor? That is intrinsic semiconductor. Number of electrons is equal to number of holes. Okay, so generally this number will be in lakhs. Okay, just for understanding purpose, I am taking only 3. Okay, so in order to increase this conductivity of this semiconductor, what I am doing is I am adding some impurities for this. I am adding here some impurities for this pure semiconductor. Which type of impurities we are going to add? Okay, so I can add one type of impurity, that is pentavalent impurities or trivalent impurities. Trivalent impurities. Okay, so here one thing is you are adding some impurities, adding some impurities, some impurities to a pure semiconductor, in order to increase the conductivity, in order to increase the conductivity, we call that procedure, adding some impurities to a pure semiconductor in order to increase the conductivity is known as doping, Okay, so doping means adding some. So what are the doping? Okay, so the type of impurities, either it may be pentavalent or it may be trivalent. Whatever the impurities we are adding, that are called as dopants. Remember, the process of adding some impurities in order to increase the conductivity is called as doping. It is called as doping. And the type of impurities we are adding, okay, that are called as dopants. Okay, so let us see here classification of semiconductors, extrinsic semiconductor. Okay, so extrinsic semiconductor is classified into two types. One is N-type extrinsic semiconductor, and the other one is P-type extrinsic semiconductor. When will you say that a semiconductor is N-type extrinsic semiconductor, and when will you say that a semiconductor is P-type extrinsic semiconductor? So for our simple understanding purpose, okay, so here let us take a pure semiconductor is there. So pure semi, here what is the condition here? Number of N is equal to P. Okay, so in this pure semiconductor, so if you dope with some impurities, okay, so if we add some impurities to this semiconductor, So which type of impurities? So if I add pentavalent impurities, pentavalent impurities, pentavalent impurities. What is meant by pentavalent impurity? In the previous class, in the outermost orbit for silicon, in the outermost orbit, we are having only 4 valency electrons, 4 valency electrons. Whereas in pentavalent impurities, we will have 5 valency electrons. What are these pentavalent materials? The pentavalent materials are arsenic, bismuth, and phosphorus. So for this means, for example, let us take arsenic. In the outermost orbit, they have 5 valency electrons. Okay, whereas the pure semiconductor, they have only 4 electrons. Here they have 5 electrons. Okay, so by adding this type of impurities, one free electron, okay, one free electron will be there. So adding a single impurity will give one free electron. So generally this type of impurities we will add in terms of lakhs. Okay, so what happened to here? Yeah, the holes concentration is same, but by adding this pentavalent impurity, we are adding extra free electron. So what happened for the condition for n-type extrinsic semiconductor is n will become very far greater than p. N become very far greater than p. So that is the condition for n-type extrinsic semiconductor. So which type of impurities you want to add? Pentavalent impurities. What are the examples of the pentavalent impurity? Arsenic, bismuth, phosphorus. Okay, so by adding this type of impurities, okay, so the number of electrons are far greater than number of holes. Okay, this is regarding n-type extrinsic semiconductor. Okay, now let us come to the p-type extrinsic semiconductor. Okay, so initially let us take a pure semiconductor. This is a pure semiconductor. What is the condition for the pure semiconductor? Number of electrons is equal to number of holes. Okay, in this pure semiconductor, so if you add the impurities, some impurities, okay, which type of impurities? Here you are going to add trivalent impurity. Here we are going to add trivalent impurity. What are the examples of trivalent impurities? The examples of trivalent impurities are gallium, indium, boron. Okay, so this type of impurities, if you add this type of impurities, so if you coming to this trivalent impurity structure, if you observe, for example, gallium is there. Okay, so in the outermost orbit, we have 3. The valence means outermost orbits are nothing but valence electrons. Okay, so in the outermost orbits, we have 3 electrons. We are having only 3 electrons. Whereas in silicon, we are having, means in a pure semiconductor, we are having 4 electrons. Here, there is only 3 electrons. Okay, so due to this adding of each trivalent impurity, that leads to one excess hole. One excess means if I add 10 trivalent impurities, I will get 10 holes. 10 holes. So what is the condition for the p-type? By adding, so generally we will add in terms of lakhs. Okay, so means here you are adding number of holes excess. So what happened to the condition here? The number of p is far greater than n. Okay, so the number of p, the number of electrons, is more. So here the number of holes is becoming, p means number of holes is becoming. So see here, In an n-type extrinsic semiconductor, the number of electrons are more when compared to number of holes. In a p-type extrinsic semiconductor, the number of holes are more when compared to number of electrons. Okay. So coming to the extrinsic semiconductor in n-type extrinsic semiconductor, what is the condition? N is far greater than P. Here in n-type, majority charge carriers are electrons. Minority charge carriers are holes. Okay. So in n-type extrinsic semiconductor, coming to the p-type extrinsic semiconductor, p-type extrinsic semiconductor, the condition, the number of holes are far greater than number of electrons. Here in p-type, majority charge carriers are holes and minority charge carriers are electrons. Minority charge carriers are electrons. Why you are discussing this? Because while you are discussing PN junction diode, while you are discussing PN junction diode, we want to know regarding what is meant by p-type material and what is meant by n-type material. So this is the brief history of extrinsic semiconductor, which will be used for next topics like PN junction diode, transistor, which is a combination of PN, PNP, and NPN. We will discuss in coming videos.